I'm the group 3 reporter, and I did the thermocouple time constant. So the objective of the lab, we really had 3 objectives. There was, we wanted to record the response of the probe when we put it into boiling and ice water. And we also wanted to record it when we removed it from the ice water and the boiling water. And then we wanted to take that data and present it and interpret it. So the theory behind the thermocouple and the time constants of the thermocouple is the time constant is defined as thermocouple, the time required for the sensor to respond to the output when subjected to a step change in temperature. So this is one of the thermocouples that we used. So to find the time constant we used the capacitance method. So in this method, our main assumption is that there's no internal thermal gradients. And we took a energy balance between the rate at which heat is convected to or from the system and the rate of change in the thermal energy within the system. Came up with this equation. So the rho is the V and the CV are the density, volume, and specific heat of the thermocouple. The H on the right is the heat capacity coefficient of the thermocouple. Delta T by delta T is the change in temperature over the change in time. And the T is your temperature time, your time response temperature in response to time, and T infinity is your ambient temperature. So we integrate this equation, you get on the left side, this is referred to as the normalized temperature. On the right side, you get the exponential of the time and the reciprocal of the time constant tau. And this is tau. And you substitute in the previous equation, you get times equal to the negative time constant of the natural log of the normalized temperature. So you can click through this like 4 times. So our apparatus that we used were the thermocouple, which was inserted into the boiling water, which was a 500 milliliter flask. It was on a hot plate to boil the water, and then we recorded it using. So our procedure was we'd open the computer to track the output readings. The readings were set to read every 200 milliseconds. For my group, which was group 3, we did the boiling water, and we brought the water to a steady boil. And then we used the bar chart on the PDAC program to confirm, before we put the thermocouple into the boiling water, we used it to confirm that the thermocouple was at room temperature. And then after the temperature, we put the probe in. After the temperature reached steady state, we removed the probe. And then in the lab manual, specified to dry off the thermocouple. And this is to remove the water so the temperature is not skewed, so that the heat transfers directly from the thermocouple to the environment and not to the water. Once the thermocouple, again, or once the probe reaches steady state temperature of the ambient, we stop the recording. So the raw data that we got, this is for the boiling water, and that is for the cooling. So this is the full process. So we can see that times in milliseconds. So from 0 to about 300,000, 325,000 milliseconds was when we were cooling, or when we were heating, and then from that point until about 610,000 milliseconds was cooling back to the ambient temperature. For the ice water, we went from 0 to about 260,000 milliseconds, and then it was removed after it reached approximately frozen, not totally because it's ice water. And then the probe was removed, and it was allowed to heat back up to ambient temperature. So, let me begin. So from the raw data, we moved T0, started at 0 seconds. And then for the removal process, I took T0 to be about 345 milliseconds or 345 seconds. So when we plotted the normalized temperature versus time, it's to scale the temperature values in order to get them from 0 to 1. And this is the plot that I got. So in an effort to linearize the data, which looking back on it now that we've already talked about it, I plotted it obviously inversely, so the temperature and I kept the normalized temperature on the y-axis and made the independent the time, which now that we talked about it should be opposite, should be flipped. And I got so when you plot this, you should get a negative tau value. So that's why I kept it, even though if you did flip it, you still get a negative tau value. And when you multiply, my thinking behind it was because you have such a small tau value, when you multiply by a large millisecond time value, you still get a normalized temperature. So that was my thinking behind it. So then that was for the insertion process. For the removal process, did the same thing, except this 0 seconds was the 345,000 millisecond, and the end was about 610,000 milliseconds. So then this was the normalized temperature, and took the natural log of that. Again, same thing, had negative value, or I had the axis flipped, but I ended up getting a time constant of 2e to the -5, and these actually, the removal process actually became more linear, and I guess that was because of either noise or the gradient when you put it in and took it out. There's that, I guess, startup process that changed that. So same thing for the ice water. This was started at 0 milliseconds from the raw data, and I took T0 for the removal process at about 310 milliseconds. So then I again plotted the normalized temperature for the insertion process into the ice water, and then also the removal that's the normalized temperature for the removal process. I then found, took the natural log of both, again, of the normalized temperature. And this, like we said before, the removal process is smoother because it was more accurate. The process of taking the temperature and measuring the temperature was more accurate than the placing it into the ice water. So to improve this, I could have removed this part to give more accurate results, and this would have, obviously from here on, looks more linear than the entire process. So in conclusion, we obtained our objectives, and questions?